Take a look at a standard traffic light. It operates on a strict, unyielding loop: green, yellow, red, and back again, running exactly the same way every single time. But out on the actual street, conditions are rarely that predictable. A pedestrian steps off the curb unexpectedly, a delivery truck blocks a lane, or heavy rain suddenly slows down traffic. Traditional computing handles problems through basic automation. It relies on human programmers to write strict if-then rules and preset timers to govern exactly how a machine behaves. The physical world is too chaotic for this approach. A programmer simply cannot anticipate and write a manual if-then rule for the infinite number of variables a machine might face in a real environment. To navigate that level of complexity, we need systems that don't rely on fixed rules. We need machines capable of analyzing their environment and adapting to new situations without human intervention. This is the exact problem artificial intelligence is built to solve. Instead of waiting for human instructions, AI uses a technique called machine learning to figure out the rules for itself. But a machine cannot learn in a vacuum. It requires a specific raw material to process, and that material is data. As we see in this visualization, instead of following pre-programmed commands, a machine learning model ingests massive amounts of unstructured data and analyzes it to identify hidden structures and predict outcomes. By processing this information, AI acts as a translation engine. It shifts computing from a system of blind instruction to one of active adaptation. Real-world data doesn't arrive in one uniform package. It comes in entirely different formats, which means AI requires specialized domains to process it. The first of these domains is data science. This field is built to handle structured data, things neatly organized into rows and columns, like numerical records, text files, and spreadsheets. Data science applies mathematics and statistics to this structured information. By crunching millions of historical records, the system can extract meaningful behavioral trends that a human analyst might miss. In practice, this means feeding a model years of neighborhood property values so it can forecast future housing prices, or having it scan millions of credit card purchases to instantly flag a fraudulent transaction. By turning raw numerical history into statistical foresight, data science operates as the analytical core of artificial intelligence. A vast amount of the world's information isn't stored in a spreadsheet. It exists as unstructured visual data, made up of raw pixels and video frames. To interpret this visual world, machines use a second AI domain, known as computer vision. Computer vision works by breaking an image down to its most basic components. The model scans the pixels to extract critical features, searching for specific shapes, textures, colors, and edges. This technical diagram illustrates how these extracted features are put to work. By recognizing specific patterns, computer vision allows self-driving cars to identify pedestrians and lane markers, or enables medical software to spot anomalies in an X-ray. It acts as the bridge between the physical and digital worlds, granting machines the ability to visually map and navigate our environment. The final major data type is arguably the most complex. Machines have to process the unstructured, unpredictable nuances of human language. This is handled by natural language processing, or NLP. It is the domain responsible for taking spoken audio and written text and translating it into a format that a machine can actually read. As seen in this infographic, NLP goes beyond simply matching words. It analyzes syntax and semantics to understand what words actually mean in context. Advanced models even evaluate emotional sentiment, allowing chatbots to identify angry complaints or recognize deceptive language in spam emails. NLP pushes computing past basic dictation. It gives machines the ability to evaluate the broader context of a sentence and determine what a person is actually trying to achieve. When we combine the analytical power of data science, the visual recognition of computer vision, and the linguistic comprehension of NLP, we create systems capable of handling many tasks that previously required human intervention. However, there is a catch. AI isn't an infallible, purely objective system. Its intelligence is strictly limited by the quality of the data we use to train it. This visualization demonstrates the concept of algorithmic bias. If a machine is trained on an unbalanced or unrepresentative dataset, It will learn those imbalances and produce unfair or prejudiced results. We see this happen in the real world when facial recognition models fail to identify certain demographic groups, or when automated systems reject qualified applicants because their resumes don't match historical, biased hiring patterns. Ultimately, artificial intelligence functions as a mirror. Our technological future depends directly on the quality of the data we collect, and it will only be as ethical and fair as the information we choose to feed it.